Hi everyone, this video is for the coursework of Pattern Recognition EEL 6825, and it describes the project of emotion recognition using Fisherface classification technique. The advisor for this coursework is Dr. Daping Oliver Wu. Let's begin. So first, let's talk about what this video is going to be about. In the beginning, I'll start from the basics of machine learning and the learning model and why we require learning at all. In the next section, I will move on to existing approaches, which will describe the work that has already been done. In the next section, I will then describe the current methodology used in this project, and I will walk you through step by step of the code and how it performs. The next section will talk about the results and the performance evaluation. It will describe how the existing methodologies work in the current scenario and how our algorithm stacks up with respect to that. And in the last section, I will talk about the conclusion, and which will include some future work and the current work being done on emotion recognition. So let us begin by talking about the components of learning and the learning model. So the basic learning problem can be formalized as follows. Given an input x, we have to find an output y, and there is an unknown target function f, which goes from the input space x to the codomain y, and there is a set of historical data which is compulsorily required for all learning models. This historical data is in the format of x1, y1, x2, y2 till xn, yn, where x1 to xn defines the historical input and y1 to yn are the corresponding outputs or the corresponding labels to those inputs. We have to find a hypothesis. The learning algorithm will pick a formula g x to y which approximates f. The algorithm chooses g from a set of candidate formulas under consideration, which we call the hypothesis set capital H. For instance, capital H could be the set of all linear formula from which the algorithm would choose the best linear fit to the data, as we will later discuss more in detail. This can be better understood with the help of an example. Say we are given the task of approving credit cards for a bank. Now we are given a set of historical data for all the customers whose credit has been approved or not approved. So our output here becomes either yes or no, a binary output, and our data contains all the customers' information, which will determine their credit score for which their approval of credit card will be accepted or denied, and the corresponding labels y1 to yn will say whether they received a credit card or not. Now we have to form a hypothesis which will take all those factors into consideration, give them appropriate weights, and our final goal will be that if that sum is greater than a threshold, then we approve the credit card or we don't approve the credit card. That can be done in a very simple linear classification model. Now our hypothesis set consists of the set of all the hypotheses from which we will choose the best fit for our g, which approximates our target function f. This hypothesis set consists of our learning model. Moving on to the next slide, let's talk about the types of learning. Now, in the previous example, our historical data was in the format of x1, y1, x2, y2, and so on. That means we had our corresponding labels for each input data. This type of learning is called supervised learning, where the output labels for our historical data is given to us, or we are given a labeled input set. There is another type of learning called unsupervised learning. Unsupervised In unsupervised learning, we are only given the historical input data. Y1 to yn is not given to us, and it becomes a much more difficult problem since we have to infer from the unlabeled input set. The third type of learning is called reinforcement learning. In reinforcement learning, the correct input and output pairs are never presented, nor the suboptimal actions are explicitly corrected. In other words, it contains the input, some output, and the grade or the confidence level for that output. In this video, since we are dealing about classification, we will mainly focus our talk on supervised learning. So let's talk about the types of supervised learning. The first type is called regression. In regression, the output y belongs to a continuous set of real numbers. Suppose we are trying to determine just the credit scores. Now, credit scores for customers have a range of like real numbers or a set of like continuous values, and if we can fit a function to that, it becomes a regression. In classification, the output is a discrete value. In binary classification, like here in this graph, the output can be either sheep or a goat, a yes or a no. That's binary classification. We can have more number of outputs, but the main difference is it will take discrete values. In this project, we will mainly talk about the classification technique for emotion recognition. Moving on to the existing approaches. The first existing approach discusses the optical flow analysis from facial actions. This approach focuses on the analysis of facial actions where muscle activities are modeled using optical flow and the displacement of feature points are measured. The first frame contains the rectangular regions enclosing the permanent facial features. These features are then tracked into the remaining sequence. Another sub-approach is to use a radial basis function neural network for each facial expression. Or we can also use a local parameterized model for each image motion for analyzing facial expression. Rigid head motions are represented by a planar model, while non-rigid motions of facial features are represented by an affine plus curvature model. This describes the optical flow analysis technique. The second existing approach is the model-based approach. The model-based approach describes a way to apply an image warping process to map face images to a geometrical model. It is based on the Gabor wavelet coefficient of 34 facial feature points, which classifies manually initialized on the face and combines them on a single vector. There are both neural network and hidden Markov model-based approaches described. A line-based caricature for facial expression classification is also described in this approach. The last way to use it is to use an active appearance model, which is also used for automatic facial expression classification. The third existing approach is fiducial point-based approach. Here, geometrical displacement of facial feature points between the current and reference frame quantify the facial movements. A hybrid model which is based on furrows and feature points is used, where a hidden Markov model is used for each facial state. Instead of a hidden Markov model, two separate neural networks can also be used. Another method is to use dual view face points, which automatically segments the facial features. Another approach is detecting 6 universal facial features while using the MPEG-4 facial definition parameter set. These existing methods are already existing in the current market, and all of them have a set of advantages and disadvantages which we will talk about later. In the next section, let's talk about our current methodology, which is divided into three parts. The first part talks about organizing the dataset. The second part talks about the Fisherface classification, where we extract the features, and the third set describes classifying the emotions into 8 categories, namely neutral, anger, contempt, disgust, fear, happy, sadness, and surprise. Let me run you through the code for organizing the dataset. As you can see, the entire project is coded in Python. The first step is to take a list of all the emotions, and our main task in this is to organize the data set. We have used the glob library in Python for this purpose. Here we are extracting the folder names, and we are taking all the source emotion, which will return all the list of all folders with participant numbers. Then we are running a loop through all the participants and storing the current participant number in the variable partic. The next step is to take another loop which will store a list of sessions for each participant, and we have another loop inside of that which iterates through all the files in that session. Then we store the current session in the variable cur, and we open each file and store it in the variable file. The next step is encoding the emotions as float, where we read the line as float and convert it into integer. Then the next step is to store the source emotions with the appropriate or directory path and the source neutral images. Then we stored the destination neutral images and the destination emotions, where we generate the path to put both the neutral image and the image containing the 7 non-neutral emotions. And we use the function copy file from shutil library in Python, where we copy from the source to the destination, which will organize a dataset for correct facial classification. The next step is to extract the faces using Fisherface classification. The first step in this is to use the 4 XML files or the HAR cascade XML files. These are predefined XML files given in OpenCV library, which allows us to correctly detect and classify faces and draw a rectangular boundary on top of it. The next step is to again store the list of emotions, and we define a function detect, which will first store all the files and get the list of all the images with the emotion. Then we iterate through the file and we open the image and we convert it to grayscale. Now the main purpose of doing this is to pre-process our dataset a bit. our face, to achieve a good accuracy, the dataset needs to be pre-processed, and so we are converting it to grayscale and then cropping it. So in this step we are converting it into grayscale and storing it in the variable gray. Then we then we detect the face using the four different Haar cascade classifiers. These are predefined parameters which need to be set, and then we go over the detected faces, stop at the first detected face and return empty if no face. The next step is to cut and save the face, where we get the coordinates x, y, and the height and the width of the face, and the size of which is the size of the rectangle containing the face. If if this is found, then if this is true, a face has been found in the file, and we cut the frame to the appropriate size, which is y till y plus h and x till x plus w. Then we resize the face so that all the images have the same size, and finally we write the image, and we pass the file if there is an error, and we continue doing so for all the files. And finally we call this function, which appropriately pre-processes and also detects the faces. The last part is to finally use our Fisherface classifier to detect emotions in our faces. The first step is to get the files, where we will define the function to get the file list and randomly shuffle it. Now, a, a good practice is to use a good ratio to split the data set into training set and testing set. In training set, we take the majority of the data set and train our model on that, and then on the minority we apply our classifier model on that to determine if the faces classified are correct or incorrect. Since we are using the Fisher face recognizer function, sorry, we will initialize the Fisher face classifier in the beginning. And then we store 80% of the dataset in the variable train and 20% of the dataset in the variable pred. Then we run a loop through all the emotions and append the data to the training and prediction list and generate the labels defined 0 to 7. Then we iterate through the training dataset, convert the image to grayscale, append the image array on the training dataset, and we repeat the same function for our prediction set. The next function is to define our recognizer function. In the recognizer function, we print our training Fisher face classifier, where we train our model based on it. Then we run a loop through the prediction data, and then we predict for each image. Then we say if the prediction is correct according to the already present labels, then we increase the count of our correct index. And this goes on for all the images, and we return a percentage accuracy, which is defined by 100 into the correct count divided by the sum of the correct and the incorrect counts. Now we run this 100 times to achieve a good accuracy, and we finally print the average accuracy. This will determine whether our model is good enough or needs to be trained more. Let's now talk about the results. As you can see here, a screenshot of the results is provided. It is difficult to run you through the code while recording this video because this model will take a lot of time to train and classify all the images in this large data set. So a screenshot has been provided for the same, and as you can see, the end score is we got 80.4% correct, which is a reasonably accurate accuracy. Moving on to the evaluation, how existing methods perform. The optical flow approach can be corrupted due to luminance variations or motion discontinuities. The model-based approach has limitations because it is difficult to design a deterministic physical model that accurately represents all the facial geometrical properties and muscle activities. The fiducial points-based approach requires manual intervention and will fail on most facial expressions that are non-binary and a mixture of two or more facial expressions. This is how our model performs. A graph has been provided which shows the classifier performance for the accuracy versus the epochs. As you can see, the accuracy steadily increases, which gives us a score of 80.4%, which is pretty good for our classifier. For the conclusion, I would like to talk about some future work and give a summary for this presentation. So emotion recognition, as you saw, is a difficult task when the data consists of only images. It is also difficult because the correct recognition of a facial emotion often depends on the context within which the emotion originates and is expressed. This classification-based example achieves a reasonably good accuracy but is slow to train. There are other algorithms using deep learning, intensive flow, and convolution neural networks that achieve a better accuracy and are faster. Capturing more complex facial behavior with, for example, a percentage of each emotion presence would make the algorithm much finer and closer to human intelligence. This sums up the video on emotion recognition and using Fisherface classification technique. This work has been done by Jahin Majumdar in the Department of Computer and Information Science and Engineering, University of Florida. Thank you.